Thank you so much for joining this lesson. We're going to discuss physics theory, paper 1. This is the exam which was done by Loreto High School, and we're going to discuss it in this session. So it's my hope that you guys are going to benefit in the program. Remember to subscribe, remember to share so that you may invite a friend. Number 1, section A, 25 marks. So number 1, figure 1, A and B shows the change in volume of a liquid in a measuring cylinder when an irregular solid of mass 102 grams is immersed in it. Study the diagram and answer the questions that follow. So we've diagram A and B here in figure 1. We can see the volume without the irregular object. Then after the irregular object has been immersed, we can see the volume changing. Determine part A, the volume of the irregular object. So we usually assume in this displacement method that the object which has been immersed does not absorb the liquid. This is water for the avoidance of doubt. So water being used here. So it doesn't dissolve water. It doesn't react with the water. Therefore now, the volume change is due to the irregular object. Therefore, what is the initial volume? We can see the initial volume is 48. Look at it this way. Right. When you look at it keenly, you shall discover that because we follow the meniscus, so it's 49, not 50. 49. So initial volume is 49. And because it's a measuring cylinder, these are cubic centimeter or milliliters. In other words, cubic centimeters. You should know lab equipments together with their calibrations. What about the final volume reading? When you check where the water is rising up to, we can see that it raises up to 99, just below 100. So we consider the meniscus, not where the water is trying to raise on the walls of the container. We consider the lowest point possible. This is 99 cubic centimeters. So volume of this irregular object shall be 99 minus 49. This gives us exactly 50 cubic centimeters. So 50 cubic centimeters. Yeah, you're supposed to show you're working very well. The density of the irregular object. We know that density is usually given by mass over volume. So with a mass of 102 and a volume of 50, then we expect 2.4 grams per cubic centimeter. And in SI unit, this can be multiplied by 1,000 to be 2400 kilogram per meter cubed. Yeah, so it can be converted to SI units. So that's how we work out number 1. Now, number 2, you can check this question in number 2. The question says that state one factor that affects the turning effect, of a force placed at a distance d from the pivot. Looking at this, you should understand that we have two factors majorly which affect turning effect is called moment, which affect the moment of a force. Two factors, that is the distance where the force is acting all the way to the fulcrum or the pivot, and again the magnitude of the force which has been applied. Now in this question, we've already talked about the distance. Therefore, it's like we're being told to mention the other factor other than distance. That will be magnitude of force. Magnitude of the force. Magnitude of the force. So that is the other factor now, which remains after we have mentioned the force. Look at number 3. Figure 2 shows a clinical thermometer, which is not graduated. Yeah, this one is not graduated. It's not calibrated. Name the part marked N. Look at that curving. And that is what we call the constriction. One is called the constriction. Then we have a part B, says state ways of making liquid in glass thermometer more sensitive. How do we make it more sensitive? One, the part M is called the bulb. That one is called the bulb. So we use a thin-walled glass bulb using a thin-walled glass bulb. You know, it's the bulb which is placed on the body whose temperature is being determined. Therefore, once you place the thermometer or the thermometer's bulb in the armpit of the patient whose temperature is being measured, then that temperature should affect the liquid in that bulb as quickly as possible or with a lot of effectiveness. And a thick wall may hinder the effectiveness. Therefore, we ensure that it is thin for easier diffusion of temperature difference, that is the heat, for heat to flow from the body to the thermometer, to the liquid in the thermometer very quickly. So that is it. We make it more sensitive, more sensitive. Yeah. Number 4, state 2 measurements that you would take in an experiment to determine the specific heat capacity of a solid. So when determining the specific heat capacity of a solid, we need the mass of the solid, very important. Mass of the solid. Then we also need temperature change. Temperature change. And remember, this is for the method of mixture. So the quantities to be measured or the measurements to be taken will depend on the method of determining specific heat capacity. Therefore, for the method of mixtures, mass of the solid, temperature change is very okay. But now, this specific heat capacity might be determined using the electrical method. So in such a case, we would need time, we would need the current, we would need voltage. Yeah, we would need voltage also. Therefore, those are some of the some of the measurements which are very key in such a task of determining specific heat capacity of a solid. All right. Now in number 5, still in section 1, remember to subscribe, remember to share with a friend so that you may invite them to this broadcast. Figure 3 shows a uniform meter rule of negligible weight with 2 weights. The 2 weights are 30 newtons, and we're also having a 50 Newton placed at 20 centimeter mark and 70 centimeter mark, respectively. Determine the position where the pivot should be placed for the system to balance. One, we've been told that the meter rule is having a negligible weight. This is to mean that the weight will not be among the forces affecting equilibrium in this case. Again, we've been told that the masses or the weights which are acting on the meter rule are 30 and 50 at 20 and 70 centimeter marks, respectively. This is an indication that the pivot cannot be placed at the center. It has to be placed closer to the 70 centimeter mark, or closer to where the 50 Newton weight is acting, simply because we have to give a bigger turning effect to 30 for an equilibrium to be achieved. The weight which is smaller requires a bigger distance, in other words, that way. So we're supposed to know that the pivot is at a point here, a known point. Therefore, this mark is not known. But what we need to know is that from 20 centimeter mark all the way to 50 centimeter mark, we are having exactly 50 centimeters there. So there is a distance there of 50 centimeter mark. 50 centimeters, in other words. We have a total distance of 50 centimeter mark. These two forces now are supposed to share 50 centimeter mark or 50 centimeters until they balance. Therefore, if we let from all right, from 20 to the pivot to be x centimeters, then we will have 50 minus x centimeters on this part. Then now for equilibrium to occur, we're supposed to know that we're supposed to understand that for equilibrium, the sum of clockwise moments should be equal to the sum of anti-clockwise moments. So the force causing anti-clockwise moment is 50 times distance. So 50 newtons multiplied by 50 minus x should be the same as a weight of 30 and the distance of x. Now there should be a balance for these two moments. 2500 minus 50x equals to 30x. Now we have to get 80x on this side, and we're having 2500. With this now, we can find the value of x by simply taking 2500 divided by 80. This gives 31.25. 31.25 centimeters. X is 31.25 centimeters. Meaning, we can now find the mark where this balance is happening. So from 20 centimeter mark, we are having a length x, which is 31.25. Therefore, the position of the pivot is going to be 20 plus 31.25. And this is going to give us, when we add 20, we get 51.25 centimeter mark. That is the point. 51.25 centimeter mark. So that's how you are supposed to work out such a question. Very easy. The next, number 6. And as we continue learning, I would like to know, how have you been recharging airtime to your phone? You can conveniently use our facility here, whereby you just go to your M-Pesa, the Lipa na M-Pesa option, the pay bill number 737356. Then the account number is the phone number that you're purchasing the airtime for. This phone number can even be Airtel, Telcom, Safaricom. Then you proceed to enter the amount that you'd like to spend as airtime. After this, you complete the transaction and you shall receive your airtime instantly. Please utilize this facility and invite a friend. Remember, you can even purchase airtime for a friend, whereby you go to Lipa na M-Pesa, the pay bill number 737356. Then after that, now the account number will be the friend's phone number. You enter the amount that you would like to buy the airtime. Then you proceed the same, and the friend shall receive airtime instantly. Yeah, that's easy. An air bubble in a hydraulic lift system would make the system to fail. Explain this observation. Remember, you were told, this is a book one actually, book one work here. You were told that one of the characteristics of a in a hydraulic system, the hydraulic systems use fluids. Yeah, and air is a fluid, but now there are characteristics of the fluid to fit in a hydraulic system, hydraulic lift system. Therefore, this fluid chosen is supposed to be incompressible. Incompressible. And remember, the system works under the transmission of pressure. Therefore, you say that air is highly compressible. Highly compressible. Highly compressible. This enters pressure transmission. This enters pressure transmission or uniform transmission of pressure from one point to the other. Highly compressible. Remember, the fluid to be used should be incompressible. Number 7, figure 4 shows a pipe of different cross-section areas, A and B. Oil flows from part A to part B. Study the diagram and answer the questions that follow. Part 1 or part A of the question 7. State the effect on the rate of flow when water flows from A to B and the rate of flow remains the same. So the rate of flow is a constant. The rate of flow remains the same. The rate of flow remains the same. Yeah, the rate of flow remains the same. Part B. State the effect on the pressure on the tube at B when water flows from A to B. The effect on pressure. What happens to the pressure of this fluid? Remember, there is variation in area and velocity. We have a big cross-section area, which translates to little velocity. So as we transition to section B of this pipe, then we shall have area reducing and consequently velocity raising. Then we know for a fluid which is flowing steadily, and its flow streamline and incompressible, then we're supposed to know that an increase in velocity, according to Bernoulli's effect now, leads to a corresponding decrease in the pressure. Therefore, because as we transition to B, there will be increase in the velocity due to decreased cross-section. There will be increase in velocity. So it will be moving very fast throughout here. Therefore, we will have pressure decrease. So pressure decreases. Pressure decreases. Very simple. Pressure decreases. Yeah. So the pressure decreases. That is the fluid flow according to, fluid flow according to Form 2 book, physics. Number 8 now. Number 8, state one advantage and one disadvantage of keeping the outer surfaces of cooking utensils like pans and soporias dull. One advantage of keeping them dull. One is to ensure that there is fast absorption of it, because you know that dull surfaces are better absorbers of radiant heat, better absorbers than what? The shiny ones. So to ensure faster, let me write it well, to ensure faster absorption of radiant heat. Since dull surfaces are better absorbers of it than shiny surfaces. than shiny surfaces. Yeah, than shiny surfaces. Dull surfaces are beta absorbers of it. Beta absorbers of it than shiny surfaces. Again, the disadvantage now comes as the contrary statement to this. We know that beta absorbers are also beta emitters. Therefore, if you leave something hot in the same sufuria or the pans, it will also cool very fast because it's also a beta emitter. Therefore, they also the utensils lose radiant heat very fast. Since dull surfaces are beta emitters. Yeah, they are beta emitters. So the better a substance or a material or a surface is in absorption, the better it is also in emission of the same heat. At number 9 now, figure 5 shows two graphs representing the relationship between extension E and force F on two springs A and B. The springs are made of the same material. Study the diagram and answer the questions that follow. So we can see that normally these two springs are obeying the Hooke's law because we can see force is directly proportional to the extension cost for the two of them. State with a reason which spring is stronger. So we can examine the two springs. Allow me to do this. If I draw a line here, then I will be able to say, assuming that we have force F, which is causing a certain extension for spring A, that force is causing an extension here, extension for A, and the same weight causes a certain extension here for B. So we can see the extension for B is greater than the extension for A using the same force. So because A can be extended with a very small extension using the same value of force, which will extend B for a very long length, then we would say that A is stronger because it can withstand a greater force. Yeah, it can withstand a greater force. Therefore, we say A is stronger. Spring A is stronger than B. Yeah, it has a greater spring constant. So in case you calculate the spring constants, you shall discover that, spring constant is a gradient from this graph. So the gradient of A is greater than the gradient of B. Yeah, that way. Number 10 now. Figure 6 shows the motion of smoke particles in a set for smoke cell experiment. Use it to answer the questions that follow. So you can see the smoke particle moving in a random motion in figure 6 there. Explain the cause of the motion in the figure 6. Why do we have random motion in the smoke cell experiment? Why do we have random motion, the smoke cell experiment? It's called the Brownian motion. We usually say that there is random motion of the smoke particles since they are being bombardment. Excuse me, bombarded. They are being bombarded or collided or hit continuously by the invisible air particles. Invisible air particles, which are also in a constant random motion. So in the smoke cell experiment, we shall have smoke cells being put in the smoke cell apparatus, whereby there is air particles there, then they are eliminated for some observations to be made clearly, and usually say that there are invisible air particles which are in a constant random motion. Now, when you put or when you introduce the smoke cells, they will also be observed to be in a constant random motion. They are in a constant random motion because they are being hit randomly by visible air particles, which are also in a constant random motion. So they set the smoke cells, the smoke particles, also in a constant random motion. Number 11. Figure 7 now shows a block of mass 40 kg resting on a rough surface. Study the diagram and answer the questions that follow. Study the diagram and answer the questions that follow. Questions that follow. So the mass is 40. State the magnitude of reaction force on the block. We know that the block is exerting its own weight. The block is exerting weight here, which is now the action force. So weight is given by mg. So we'll talk about 40 by 10, giving us 400. One thing we should know about reaction and action is that reaction is always equal to action, but acting in the opposite direction. So we will have a reaction equivalent to the action caused by this block. So if it is acting on the surface with 400 Newton, then the surface will offer a reaction equivalent to 400 Newton. That is it. Number 12 now. We are moving. A sample of water is heated steadily from a temperature of 0 degrees Celsius to 10 degrees Celsius. On the grid provided in the figure 8 below, sketch a graph of volume against temperature for the sample of water between the temperatures 0 and 10. So we're supposed to know that there is what you call between 0 and 4 degrees, there is what you call the anomalous expansion of water, whereby when you heat, instead of water increasing in volume, it decreases. So we will have a sketch now here such that if initial volume is at that point, we will have a decrease as you continue increasing against the temperature. Sorry, this is supposed to be temperature. Sorry. It's supposed to be temperature. I think they did a mistake there. They're typing, sorry. Temperature in degrees Celsius. Therefore, are we talking about now, instead of the volume increasing with temperature, we will have decreasing until at 4, whereby now it behaves normally. Now beyond 4, increasing temperature increases the volume. Therefore, you discover that this normalized expansion now is happening between 0 and 4. So this will be 4 degrees Celsius. So at 4 degrees Celsius, then we will have now the change whereby now water starts behaving normally. But between 0 degrees Celsius and 4, when you increase temperature, for any substance, we expect an increase in volume. We expect an expansion, but water behaves abnormally. We call it the anomalous expansion of water. So that is the curve that we expect. State one application of Pascal's principle. A student should be in a position to state the principle first, that a pressure applied at one point in an enclosed fluid is transmitted equally to all the parts of the enclosed fluid. And so some of the applications is that it can be used in hydraulic machines. So hydraulic lift uses this. We can also talk about the hydraulic brake system, among other applications. Now we talk about section 2 of this paper. Yeah, section 2 of this paper. The figure below shows section B, 55 marks, which are also compulsory. So we go now bit by bit as we answer these questions. The figure below shows a heating curve of solid X. Study the diagram and answer the questions that follow. We heat solid X from A to E. Time in minutes, temperature in degrees Celsius. Explain the shape of the graph between B and C. So you can see we are heating and there is a gradient showing increase in temperature with the time. But now between B and C, there is no change in temperature, but the time is increasing, but temperature is not changing. The graph flattens. That is melting. So we say that the solid melts in region BC. The solid melts. Therefore, the energy or the temperature, the heat energy, yeah, let's use heat energy. The heat supplied, does not change the temperature. Rather, it breaks the forces. This is to break the bonds holding the solid particles together. Solid particles together. Yeah, the solid particles together that way. Then between D and E, we can see again there is some flattening, increase. Now from C to D, it has become a liquid and it is absorbing heat energy. And we can see there is temperature change between C and D. So the liquid is absorbing heat energy. But D and E, there is what we call vaporization. So it has become a liquid. So the substance vaporizes. The substance vaporizes. And we follow the same explanation that the heat energy supplied within that time does not change the temperature of the liquid. Rather, it is used to break the bonds holding the liquids together, the liquid molecules together until they join the gaseous form. Look at part B. We are told to define the term specific heat capacity, of course, of a substance. This one refers to the quantity of heat energy required to raise the temperature of a unit mass of a substance by 1 Kelvin or by 1 unit. The amount of heat energy, we can actually say the amount of heat or the amount of energy required to change, the temperature of a unit mass, very key, a unit mass of a substance by 1 unit. Remember, when you don't say unit mass, then you will be defining something else and you'll become wrong. So you should write definitions very carefully. At part C now. A block of metal of mass 150 at 120 degrees Celsius is dropped into a lagged calorimeter of heat capacity 40 joules per Kelvin, containing 100 grams of water at 40 degrees Celsius. So calorimeter and water are at 40 degrees Celsius, while a metal block is very hot at 120. Now it's being dropped. The temperature of the resulting mixture is 46, taking specific heat capacity of water to be 4200 joules per kilogram per Kelvin. Determine part 1, the heat gained by the calorimeter. The heat gained by the calorimeter. So heat energy, the heat energy will be given by specific, okay, heat capacity times change in temperature. Heat capacity times change in temperature. When specific heat capacity is not provided, then heat capacity will be provided, and the quantity of heat energy absorbed shall be heat capacity multiplied by change in temperature. So we multiply this by change in temperature. The calorimeter is changing in temperature to 46 from 40. So we're multiplying 40 by 6, in other words. This gives us 240 joules of energy. 240 joules. Joules capital J. Heat gained by water. Now, for water, we are given the mass and also specific heat capacity times the change in temperature. So we shall talk of mass of water. Mass of water, 100 grams. So we make it 0.1 kg, because mass should be in SI units, times 4200 times change in temperature. Again, water is varying from 40 to 46. So we also be multiplying by 6 as the change in temperature. 0.1 multiplied by 4200 multiplied by 6. And this gives us 2520 joules of heat energy absorbed by water. Look at part 3, the heat lost by the metal block. The heat lost by the metal block. This one we can answer in 2 different ways. Heat lost by the metal block, we can say numerically, heat gained by metal block equals to heat absorbed by both the water and calorimeter, because the calorimeter is well lagged. Therefore, no heat losses to the surrounding. This is to mean that all the heat energy lost by the metal block has been absorbed by both calorimeter and water. Therefore, we can say heat lost by metal block, heat lost by metal will be equal to the summation of 240 and 2520. Yeah. So when we add 240 to this value, we'll be getting 2760 joules. That is it. This can also be answered as an expression, whereby we can say that the metal block mass is known, 150, initial temperature is known, and final temperature is known. Therefore, we can say that it is only the specific heat capacity which is not known. So we say the quantity of heat will be mass of the metal times specific heat capacity of the metal times temperature change for the metal. So the quantity of heat will be given by 150, we change to kilogram, 0.15 multiplied by unknown specific heat capacity multiplied by from 120 all the way to 46. So this is going to be 120 minus 46, that gives us 74 times 0.1415, that is. So 11.1 multiplied by the unknown specific heat capacity of the metal. Therefore, now we say this heat energy, specific heat capacity of the metal block now should be determined. Specific heat capacity of the metal block is what we are now determining. So we would say at this point that the specific heat capacity of the metal block is going to be given by the heat energy. We say mathematically, heat lost by metal equals to heat gained. Heat gained by water plus heat gained by the calorimeter. Yeah. Therefore, 1.1 times the non-specific heat capacity should be equal to 2760. So how do we remain with specific heat capacity of the metal? It shall be, we take 2760 and we divide by 11.1. This gives us 204.8.65. Being specific heat capacity, we'll talk about joules per kilogram per Kelvin. Joules per kilogram per Kelvin. That way. Part D of the same question. Part D of this particular question. Part D is telling us that the boiling point of water is normally 100. State any two conditions that would change the boiling point. One condition would be change in pressure. Change in pressure. Then two, we also talk about a presence of impurities in the water. Of impurities in the water. Assignment, we know that impurities affect boiling point and the melting point of substances. We know that pressure affects boiling point and melting point of substances. Please do a research on how each affects melting point and boiling points. Make sure you do that research. 15 now, part A. Yeah, we are still in the section 2. Still in the section 2. And here we are not joking. We are doing every bit the way it should be done. In an experiment to determine the density of a liquid, a uniform cylindrical metal rod of cross-sectional area A equivalent to 127 square centimeters was hung from a spring balance and lowered gradually into the liquid. The upthrust for various submerged heights was determined. The results obtained are shown in the graph. We know that there should be a direct proportion there. Yeah, direct proportion because upthrust is the weight of displaced liquid. Therefore, if upthrust is the weight of displaced liquid, then we should know that the longer the height we submerge, the greater the upthrust to be experienced. So we can see the graph upthrust in newtons against submerged height. The height is times 10 power negative 2 meters. From the graph, determine the slope of the graph. Determine the slope of the graph. In other words, determine the gradient. So we just need some two coordinates. I'm trying to examine this graph and the calibrations used in the graph. Sorry, it might not be very clear, but be sure that I'm going to analyze it well. So we can use some coordinates here. Use some coordinates there. So we shall work with the values that I'm going to extract. change in y over change in x. We just need the gradient, in other words. So coordinates that we are having are 4 times 10 power negative 2. And on the y, we have 0.5 newtons. Another coordinate at this point, we can talk about, is that one 1 and 0.1? Is that 1 and 0.1? Yeah. 1 against 0.1. So this is not 1. And this is going to be 0.8 against 1. So 0.8 times 10 power negative 2 against 1. That way, against 0.1, sorry. Against 0.1. So we have two coordinates there. We need, if we take 0.5 and we subtract 0.1, this one should be divided by 4 minus 0.8. And you remember that here we are having times 10 power negative 2. So 0.4 out of, when I take 4 minus 0.8, I'm having 3.2. And here there is times 10 power negative 2. You must be very careful with interpreting the axis. So 0.4 divided by 3.2, then we divide further by 0.01. That is 10 power negative 2. This gives us 12.5. 12.5. Now it's good you find gradient together with the units. So on y we are having newtons, then meters. So Newton over meters. Newton per meter. Yeah. Newton per meter. 12.5 Newton per meter. The value we're also finding again in part 2. Find the value of the constant rho, that is the density, given that the equation of the graph is u equals to, remember u has been plotted on the y-axis. Then on the horizontal axis, we are having height. We are having height, which is a length. We are having height, which is length. Here, height, which is length. That is what is on the x-axis. Therefore, ours is to analyze this equation now using a gradient of a straight line. Y equals to mx plus c. Our c is 0 in this case because c should be the y-intercept. The line is cutting the y-axis at 0. You see where the line passes? The origin. Therefore, we will say that this one is usually the slope. So whatever is the coefficient for the quantity on the x-axis becomes our slope. Therefore, we will say that slope, according to the graph, slope equals to, our gradient equals to whatever multiplies h. That is A times density times G. That becomes our slope. Therefore, our slope of 12.5 is equivalent to cross-section area has been found. We make it as a unit. That one is known. 5127, we divide it by 10,000. So 51 what? 27, yeah. 5127 as the cross-section area becomes 0.5127 just to be divided by 10,000 multiplied by unknown G multiplied by unknown rho 10 times G. So the slope is the the values that multiply the quantity on x-axis, and the slope is known. So how do we get density now? We have to divide 12.5 out of 0.5127 multiplied by 10. This gives us exactly 2.438. 2.438. 2.438 grams per cubic centimeter. Yeah, grams per cubic centimeter that way. So with this now, we can say that the density can also be given in SI units. Yeah, in SI unit. Huh? And actually, this is in SI units. Sorry. Actually, this is supposed to be exactly in SI units. Let me check again the replacement. Because we are dealing with SI units, the density cannot be in grams per cubic. We have converted everything. So it's good for us to remember that we divide this one by 1,000,000, not by 10,000. Converting from cubic square centimeters, we just check again. I'm converting the cross-section area from 5127 to meters squared. Yeah, I think I divided well there. 0.5127, 0.5127 multiplied by a known density. Then we multiply by known G, known value of G. Known value of G is going to be, so when I divide here, I'll be talking about 12.5 divided by 0.5127 and also 10. This becomes 2.438. 2.438. So this is the value that we shall work with. 2.4 times 10, 2.4 kilograms per meter cubed. That becomes our density. Yeah, that becomes our density now. That exactly becomes our density. It becomes our density. Okay, part B. Part B. One of the practical applications of the law of flotation is in hot air balloons. State 3 ways through which greater upthrust is achieved in balloons. So to ensure greater upthrust, we ensure that the balloon contains a gas with a very low density. The balloon contains a low density gas. The balloon contains a low density gas. Then the material of the balloon is made of a fabric with low weight. The balloon fabric, in other words. The balloon fabric has low weight. Then we also say that the balloon is wide. The balloon is broad. Is broad so as to displace maximum air or much air. And that one is what increases the upthrust acting on the balloon. Part C. The figure below shows a pendulum swinging between points P and R, passing through the main position Q. Study the figure and answer the questions that follow. It's an illustration of a simple pendulum. Okay. Describe the energy transformations which take place when the pendulum swings from P to R. So we say that at P, the pendulum has maximum gravitational potential energy, and zero kinetic energy as it moves to Q, that is going downwards now, it loses the gravitational potential energy and gains, or as it gains kinetic energy, to have maximum kinetic energy at Q. So as it passes Q, it will have maximum kinetic energy and at the same time, zero potential energy. As it rises up, from Q, it starts immediately losing kinetic energy and gains potential energy to have maximum potential energy at R. So by the time it's going to R, it will arrive there with maximum potential energy and zero kinetic energy. And zero kinetic energy at R. So by the time it's going up to R, it will have zero kinetic energy. Remember, gravitational potential energy is usually given by mgh. Therefore, the higher the object goes, the greater gravitational energy it will possess. So at P and not moving, it is having the greatest or the maximum gravitational potential energy. Kinetic energy on the other side is given by half mv squared. Therefore, at P, when it is not moving, it is having zero kinetic because velocity is zero. V is velocity. Velocity is zero at that point. But immediately it starts swinging. It starts gaining some velocity and some momentum, such that now velocity starts increasing. And remember, as velocity increases, the height is reducing. So with reducing height, there is loss in gravitational potential energy. And with increasing velocity, there is increase in kinetic energy. That way. The pulley system shown in figure 8 is used to lift a load of 40 newtons through a height of 2 meters. Through a height of 2 meters. Very sensitive for you to underline some statements that you continue learning. So the pulley system here can be seen. Given that the effort applied is 30 newton, determine part A, the velocity ratio of the pulley system. So we have two ropes here supporting the load. Therefore, VR shall be 2. VR has no units. It's just a ratio. 2. Work done in lifting the load. So the load is 40 newtons and it's going to a height of 2 meters. We know that work is given by force times distance. So a load of 40 and 2 meters will give us 80 Newton meter, or simply joules. Yeah, Newton meter, force times distance. Look at part C, work done by the effort. Work done by the effort. So work done by the effort is going to be, the effort is 30 Newton. So we will say that work done again here should be force times distance, a force of 30 and a distance of 4 meters, 120 Newton meter or simply joules. The reason we're using effort distances for, we're supposed to know that velocity ratio is given by distance of effort out of distance of load. Now, 2 is given by, because the velocity ratio is already known, 2 is given by distance of effort out of the distance through which the load is going to raise. So distance of effort will be 2 times 2, which is 4 meters. That way. 2 meters that way. Aha. There are 4 meters. Efficiency of the system. So this system now is having some efficiency. And you know, we're supposed to talk about efficiency now being given by work output divided by work input times 100. Output, the work on the load. Input, the work the effort does. We express this as a percentage. And we are going to get exactly, yeah, you can work out that. We are getting exactly 66.67%. So that is now the efficiency of this particular system. With work, energy, power, and machines, you're supposed to be that careful. Must know every formula. You must know what you call velocity ratios of different machines. Yeah, different machines. Number 17 now. A stone is whirled with uniform speed in a horizontal circle having a radius of 10 centimeters. It takes this stone 10 seconds to describe an arc length of 4 centimeters. Determine part 1, angular velocity, W. We're supposed to know that angular velocity is given by V over R. So how can we get velocity? Remember, we are given 10 centimeters is being covered in, 4 centimeters is being covered in 10 seconds. Therefore, we can say distance over 10. This is 0.004 meters per second. Therefore, for us to get omega now, we need to talk about V out of R, a radius of 10, 0.1. This shall be 0.04 meters per second. Not meters per second, sorry. This one being angular velocity should be radians per second. Yeah, radians per second for that too. We are also needed to calculate period T. We know that omega can also be given by 2 pi out of periodic time. Therefore, how do we make periodic time the subject? By taking 2 pi out of omega. So 2 multiplied by 3.142. This one now should be divided by the omega that we've just gotten, 0.04. Yeah. So 2 multiplied by 3.142 divided by 0.04. This gives us 157.1. 157.1 seconds. That is the periodic time. That is the periodic time. Part C. Let's look at this. A glass capillary contains enclosed air by a thread of mercury 30 centimeters long when the tube is horizontal. The length, when the field is horizontal, the length of the enclosed air column is 48 centimeters as shown. What is the length? Look at this now. What is the length of the enclosed air column when the tube is vertical with the open end uppermost if atmospheric pressure is 750, open end uppermost. When it looks like this now, what we expect to be the length here. So the mercury thread is going to be here. It is still 30. And now we have a new H. This height is an application actually of what you call the Boyle's law of an ideal gas. And we talking about the heights of the air column representing volume. So we know that pressure 1 times volume 1 equals to pressure 2 times volume 2. So what is pressure 1? In the first case, because the weight of mercury thread is acting downwards, then the pressure acting here is only pressure due to atmosphere. That is 750. Yeah, 750 millimeters of mercury. Then volume 1 is the height, 48 centimeters. What about pressure 2 in the second case now? Pressure 2, since the open end is uppermost, then atmospheric is acting downwards, and also the weight of mercury is also acting downwards. So we need now, 30 centimeters is the same as 300. So it will be 760 millimeters plus 300 millimeters of mercury. Then we can talk of volume 2 now, which is the new height, which is not known. So according to the mathematical expression of Boyle's law, we can find this new length, which is of course going to be smaller because it is now being compressed by a bigger pressure. It's an addition of the mercury thread and also the atmospheric pressure. So 750 multiplied by 48 should be equal to uh-huh 760 plus 300 multiplied by unknown h. So we can get the h now. Use my calculator. Plus 300. So we take 750. Just a minute. It's 750, not 760. Sorry. 750. So this is 750 also. So we take 750 plus 300. Then we say now 750 by 48 divided by 1050. This is giving us 34.29. Centimeters. This is the column of air now. The column air has been calculated very effectively. Can we talk about Roman 2? Let us see. Explain why mercury does not run out when the tube is inverted with the closed end. When we invert this way, the mercury thread is going to be here, air shall be here, and atmospheric pressure shall be acting there. Why does the mercury thread not flow out, in other words? This is because the pressure due to atmosphere, or atmospheric pressure due to atmosphere. Sorry, let me check. The pressure due to atmosphere is greater than both the air pressure in the tube, the air pressure and the mercury in the tube. So the pressure of the air is acting downwards, the pressure of the mercury is acting down, but atmospheric pressure overcomes both of them. The atmospheric pressure overcomes both of them. Problem 2, explain why an air bubble increases in volume as it rises from the bottom of a lake to the surface. This again, Boyle's law. We say that pressure of air, pressure of water, since it's a liquid, increase with depth. So we say at the bottom, pressure is high or higher. Hence, the bubble has a small volume. So as the bubble comes up to the surface, then we will have the column of water reducing in the lake. And so some little pressure of water will be acting on the bubble. And now the air bubble shall be seen becoming greater because it is not being compressed by a big pressure. Okay. When an inflated balloon, look at this now. When an inflated balloon is placed in a fringe, it is noted that its volume reduces. Use the kinetic theory of gases to explain this observation. A balloon is seen to decrease in volume when placed in a fridge. So the low temperatures, the low temperature in the refrigerator lowers the kinetic energy of the air particles in the balloon, making them vibrate less or vibrate within a shorter distance. Hence, occupying a smaller space because they are now not vibrating to within a longer distance. The vibration is not within a longer distance. Therefore, we will have the air particles occupying a very small space to it. Look at V now. Look at V. A certain mass of hydrogen gas occupies a volume of 3.2 meters cubed at a pressure of 1.5 times 10 power 5 pascals and a temperature of 22 degrees Celsius. Determine the volume when the temperature is 0 degrees Celsius at a pressure of 8.0 times 10 power 4 Pascal for 3 months. This is a combined gas equation, which says that PV over T, PV out of T should be P2 V2 over T2 that way. What is the first pressure? 1.5 times 10 power 5 times the first volume, which is 3.2, divided by the first temperature, which is supposed to be absolute temperature. So 22 plus 270, 3, we get 295. We have to convert to SI units, equals to the second pressure, which is 8 times 10 power 4, multiplied by the new volume, which is now unknown, volume 2, out of the second temperature, which is 0, and 0 is 273 Kelvin. So now from this, we can get the second volume after computing, and we get 5.553 meters cubed. So that is the volume. So we just remain with V2. We can multiply sides, both sides by 273 over 8 times 10 power 4. And we get the new volume. So this is the equation to work in such a case. Number 18. Yeah, number 18. We are almost concluding. In number 18, we are told that a car goes round a flat circular bend whose radius is 50 at a constant speed of 30 meters per second. Calculate its acceleration. You know, this one should now be called centripetal acceleration. Calculate the centripetal acceleration, because the car, even if the speed is constant, it's said to be accelerating. So acceleration, which is called centripetal, is given by V squared over R. So 30 squared over R, 50. And this is giving us 18. Yeah. Meters per second squared. That is the centripetal acceleration. If the mass of the car is 1200 kg, calculate the frictional force required to provide the acceleration. Centripetal force required to the frictional force required to provide acceleration. So the frictional force is the one that brings centripetal force. And this is given by mv squared over r. Remember, v squared over r is what has already been calculated. So F, frictional force, is going to be frictional force, which is the centripetal force in this case, shall be given by m. V squared over r is 18. And this is going to be 21,600 Newton. Yeah, 21,600 Newton, according to uniform circular motion. Then we have a part C here. Calculate the maximum speed at which the car can go around the bend without skidding if the coefficient of friction between the tires and the ground is 0.5. So we know that a frictional force is usually given by the coefficient of friction times the reaction force. So we will say that times the reaction, which is mg, of course, which is a mg. Therefore, we shall talk about the force now being 0.5 times the reaction caused by this car. The reaction caused by this car is remember, the mass is 1200. So now the weight it has is 12,000. So this is 6,000 Newton. Then now we will say that 6,000 Newton is given by mass times V squared over a radius of 50. Yeah, a radius of 50. So how do we get V squared? We need to multiply 6,000 by 50 over 1200. This gives us exactly 250. So that V will become the square root of 250, and that's 15.81 meters per second. 15.81 meters per second that way. Then look at this. Give a reason why the driver of the car has to move through the same bend at a lower speed during a rainy day. This is because we have reduced friction. When it is rainy, when it's muddy, friction is reduced. Thus, centripetal force is less. To avoid skidding, in other words, since friction is reduced. Remember, it is this friction which will provide centripetal force. Therefore, friction is not there when the ground is muddy. That becomes our last question. Thank you so much for following. Remember to subscribe and share with friends. See you next time for a paper 2.